Good morning, everyone. Morning session, first speaker of the morning session is Harald Upmeier from Marburg, Germany, University of Marburg, Germany. And he's going to speak on analysis and T-wise expansion of Kepler manifolds.
Thank you very much, especially to the organizers for inviting me to this wonderful place. So as you already see from the title, this talk is more in analysis on Hermitian symmetric spaces. But in the beginning, first part, I have some nice algebraic geometry, I think, results on algebraic geometry in this setting. So let us first explain what do I mean by Kepler manifold. And then we come to the TYZ expansions a little later. I guess the concepts discussed here are not unfamiliar to most of you, so I will be happy to provide the slides if someone is interested. So let us first look at a classical Kepler variety, is sometimes used in geometric quantization in a simple setting. Namely, we take capital Z, this is usually my symbol for a complex Hermitian vector space, Cn plus 1, and look at the quadric Z sub 1. The sub 1 means something, it means rank 1, namely the full vector space has kind of rank 2, as I will discuss later. All vectors such that z0 squared plus zn squared is equal to 0. So, in a sense, a complex light cone. It has a symplectic interpretation as the cotangent bundle of the sphere without the zero section. So, the cotangent bundle is all pairs x, xi of vectors of norm 1. X has norm 1, is in the sphere Sn. Xi is a vector different from 0 because we remove the zero section. And cotangent bundle, the condition is that they are perpendicular. X, xi is 0. It turns out if you make this complex, so if you write z x plus I xi halves, then you get precisely the condition z0 squared plus zn squared equal to 0. So it's a canonical identification between z sub 1 and the cotangent bundle. Well, this is the cone over a contact manifold, the cosphere bundle. And this I call S sub 1. This symbol I will use repeatedly. The sub 1 is the same index as Z sub 1. So it's the cosphere bundle, the same setting as above, x, xi, but both vectors have now norm 1 and are perpendicular. And the identification is again Z is x plus xi halves. And trivial, we have kind of a polar decomposition. Namely, the cotangent bundle without the zero section is R plus, the positive half line, times S1, of course. You can always normalize. So S1 is kind of the base and R plus is the fiber. Well, the varieties that I will look will be a little bit more general, namely for higher rank. This example was of rank 2. I will explain what I mean by this later. So let us look at a higher rank situation. Namely, let's look at all matrices of type R by S. Could be rectangular, although the square part is the important case, of course. So R is less or equal to S. That means the rank is R. And fix an L between 1 and R, so up to the rank. Then I define Z sub L. We had L equal to 1 in the first case. All matrices of rank less or equal to L. That is, of course, an algebraic variety and a fine variety defined by the vanishing of all minors of order L plus 1. not only the principal minors, that's not enough, but all minors all block minors that you can have of order L+1. That is easy. It has singularities, and the regular part that is with a circle on top, I hope this is legible, ZL circle, the regular part of that variety, is all elements where the rank is equal to L. So it is precisely Z sub L minus Z sub L minus 1. That's the regular part, and the ZL minus 1 is the singularities of Z sub L. So previously we had L equal to 1. Let us write this down in this case. Z sub 1 would all be all matrices of rank less or equal to 1. Vanishing of all 2 by 2 minors. And the regular part is just, the only singularity is the origin in this case, point singularity. Now in the previous slides we had also an S sub 1. So what would this be in this case? Well, these are all rank 1 operators. You know, the physicists like to write them as dyads, psi tensor eta star, where xi is an R vector and eta is an S vector, both of norm 1, of length 1. That's the S sub 1. And of course, again, every rank 1 operator is a multiple in a unique way, more or less, of S sub 1. So we again have a polar decomposition. Here I've spelled it out only for L equal to 1, because for higher rank it will be a little bit more difficult, as we will see later. Rank L equal to 1 is always the simplest case. I mentioned already that I will discuss Hermitian symmetric spaces of arbitrary rank. That is my main specialty, of high rank. So let us introduce Hermitian symmetric domains in more detail. We really need the fine structure of Hermitian spaces, symmetric spaces. So capital Z will again be a complex vector space, as always in my talk. And D will be any bounded domain to begin with. Then there is a famous group associated with it, namely the biholomorphic automorphism groups. So all holomorphic mappings from D to D, which are bijective, and then one can show the inverse is automatically holomorphic by a deep theorem, not of Élie Cartan, but Henri Cartan. This is a real Lie group of finite dimensions. It's funny, normally diffeomorphism groups of manifolds or symplectomorphism groups are infinite dimensional, but in the complex setting, it's finite dimensional. It's almost like linear. This domain is called symmetric if this group acts transitively, that is, then it would be called a homogeneous domain. And in addition, around each point, there exists a symmetry S sub O, which is an involution and has isolated fixed point O. One can show that the existence of a symmetry around every point already implies transitivity. Products of symmetries generate a transitive group already. Harishchandra worked, of course, on representations of semi-simple Lie groups related to the symmetric domains, realized that every Hermitian bounded domain can be realized as a circular domain, invariant under the circle group. I think it did not prove convexity, but it is true that you can always make it convex. It's sometimes called the Hermann convexity theorem, but it's basically the Harishchandra realization as a convex circular domain. So it is a unit ball. But be careful, it's not a unit ball of a Hermitian metric, but of a norm. In a norm, it has a non-smooth boundary in general. So this norm is essentially unique. It's called the spectral norm. The notion will become clear in my next example. And if you use the Harishchandra realization, as I will do from now on, the stabilizer at the origin, which is of course part of the domain, will become linear. That is unusual, but the case linear. G, of course, is not linear. because it must act transitively, so it must move the 0 to any other point. But K becomes a linear group. It becomes compact. That's always the case with symmetric spaces, consisting of linear transformations. So D is equal to G mod K. If these domains have rank bigger than 1, where the rank is defined as the difference of rank G minus rank K, then the domain will not have a smooth boundary. So this is maybe somewhat unusual. Most people like smooth boundary for obvious reasons. So D is pseudo-convex. It is even convex. It is a domain of holomorphy, but not strictly pseudo-convex if the rank is bigger than 1. So that is the main reason why we need elaborate theory to define the geometry and then later the analysis on these domains. So let's see a basic example that in a nutshell shows everything. The matrix ball. We had this example already before, namely all R by S matrices. But now I endow it with a norm, the norm that we all know from linear algebra, namely the operator norm in the sense of matrices. That means the norm of the absolute value of the largest eigenvalue of the absolute value of Z. So spectrum of ZZ star to the 1/2 and the supremum. And we all know it's kind of hard to compute this operator norm, but it is a norm on the matrix space. So we define the matrix unit ball, D. These are all matrices of norm less than 1. Well, nobody wants to compute the spectrum all the time, so we can make it a little simpler, namely all matrices such that the identity minus ZZ star, that will be a square matrix, identity minus ZZ star, is positive definite. It's the same condition, just you avoid talking about eigenvalues and so on. So that turns out to be a convex domain, of course. It is symmetric. Transitivity has to be proven, of course. It's not clear that it is homogeneous under holomorphic transformations. But of course, projective geometry helps us in this respect. The transitive group is the so-called unitary, pseudo-unitary group of type R, S, URS. This means all block matrices A, B, C, D in GL R plus S such that they are unitary with respect to the degenerate form 1, 0, 0, minus 1, which acts on the domain via Möbius transformations. You know this from classical function theory, but here it's matrix valued AZ plus B times CZ plus D inverse. What is the maximal compact subgroup? Well, I promised it's a linear group. And the group K is precisely fixing the origin. If you put this into the Möbius transformations, it means that B and C are 0, so only A and D are left. It's the block diagonal matrix, and in fact acts linearly. Z goes to A, Z, D star, D inverse, but it's the same as D star since we have unitary matrices. So that is, in a nutshell, a basic example. But it is not the only one. Symmetric spaces are more complicated than just matrices. Well, because they are more complicated, we need more machinery. And there are two schools, one very widely used, namely the Lie theoretic approach, using root systems and all the semi-simple Lie theory. But Max Köcher realized in the 50s or 60s that there is also a more direct approach to symmetric spaces, which works best in the Hermitian case, not in the real case. In the Hermitian case, using Jordan algebras. So part of my talk and my aim is to introduce you and make you hopefully interested in Jordan theoretic concepts, which are very beautiful, which were originally invented to treat modular forms, so discrete subgroups and modular forms, so they still have a lot of potential. But here we go very slowly. So again, as always, Z will be a complex vector space, and we start with a ternary composition. Z cross Z cross Z with values in Z. So it's not an algebra product, which would be a binary composition, but a ternary. But this is very familiar for you as differential geometers, namely the Riemann tensor is a ternary. It depends on 4 indices, but if you make it vector valued, it becomes a ternary product. The Riemann tensor, curvature tensor, and that is exactly what happens here. This ternary product will be part of a Riemann tensor. Well, but right now it's just a trilinear composition. Well, we have to be a little careful. First of all, the notation, it's traditional. It's not very beautiful notation, x, y, z. So let me write it down. It does not mean a set x, y, z. These brackets should remind you of anti-commutators. The physicists, they use anti-commutators. They like anti-commutators over commutators, and they use this notation, this braces. So that's the reason why this is the notation for the ternary product. It's not very beautiful, I agree. Well, we have to be a little careful. It is bilinear in the outer variables, and even symmetric there. I talked about anti-commutator, so anti-commutator is of course symmetric, but in the inner variable, in the y, it is conjugate linear, so a little bit difficult. We introduce an endomorphism D of x comma y by fixing the first 2 elements. So it's like a multiplication operator, but you have to fix 2 elements to make it a multiplication because we have a triple product and not a binary product. Okay, now the first more technical identity, we call Z a Jordan triple of Hermitian type if 2 things happen. First of all, a certain identity, the so-called Jordan triple identity, which by the way will play no role for the rest of my talk, is satisfied, namely the commutator of 2 such D operators, dxy and duv, is a difference. So this means essentially that the Lie algebra generated by the D's is closed under Lie bracket. The D's, the linear combination of D's become a Lie algebra. That is what this says. So D depends on xy, D depends on uv, and of course, on the other side, they must show up again, the vectors x, y, u, v, and that is the formula. This is actually a kind of Jacobi identity. If I had time, I could explain in more detail. It is related to Cartan's theorem that the Lie group, out D is a Lie group, and so on. So that has to hold. As I said, it will never show up again, but in addition, we take the trace form. You would take the killing form for Lie algebras. Here it is the trace form of the D of xy. dxy is an endomorphism, has a trace, must be positive definite. So this, one should say it's a positive definite Hermitian Jordan triple, but we just abbreviate it as Hermitian Jordan triples. So 2 conditions. One is like an algebraic condition of Jacobi type, derivation identity, so to speak, and then positive definiteness of a certain Hermitian form. And Max Köcher proved that every Hermitian symmetric domain becomes the unit ball of a Hermitian triple in a unique way. Conversely is also true. If you start with a Hermitian Jordan triple, the unit ball becomes symmetric. That is marvelous. It's the Lie theorists can only say a symmetric space is G mod K, where G is a semisimple Lie group. But we know that semisimple Lie groups occur in a variety of cases, and it's rather complicated. Here we prove that the domain directly becomes a unit ball, and the tangent space, the capital Z, becomes kind of the tangent space, of course, at the origin, for example, has a triple structure. As I said, it's kind of a curvature condition, which is positive definite because we have a bounded domain. Otherwise, we would get unbounded domains. And in this case, the group K, that plays a major role from now on, consists of all transformations preserving the triple product. So it's not algebra automorphisms, but triple automorphisms. You know, it cannot be, it does not fix the unit element. if we come from the examples before, but it preserves the triple product, this XYZ triple product. So let us show how they all look like. By Köcher's theorem, classification of Hermitian domains is the same as classification of these Jordan triples. So that is a question of pure algebra. And the list is short. It has essentially three parts. The first case are the matrix triples. So we already had this as our basic example. We take all R by S matrices. Now here the triple product is just xy star z plus zy star x. Very simple triple product. Clearly it is symmetric in x and z and anti-linear in y. The group K, the triple automorphisms we knew already from our previous slide, is the product of UR cross US. The rank, of course, is less or equal to S. And here I introduce two numbers A and B. This is just to express later theorems. These are kind of the so-called characteristic invariants. In the complex case, A is 2. Let me not define the A, is a little technical. And the B is S minus R. So B is 0 if S is equal to R, if in the square case. So A is equal to 2 is, in a sense, the complex case. The simplest of all matrices is, of course, if the rank is 1, then we just get a Euclidean vector, a Hermitian vector space of dimension D, and the triple product that I had, xyz is xy star z plus zy star x, becomes simpler. It is expressed in terms of the inner product. If the rank is 1 and K is just a unitary group. Well, we also have the real case, A is equal to 1, namely symmetric matrices. They are still the complex symmetric matrices, but the multiplicity is 1. This is called the real case. We also have antisymmetric matrices. They are closed under this triple product. You know, antisymmetric matrices do not form an algebra or so, but they are closed under the triple product. Here A is 4. It's kind of the quaternion case. I will explain this notion a little more detail in the next slide. So this is the first case, the three matrix types. All matrices, rectangular matrices, and symmetric and antisymmetric case. Then we have in rank 2, that was my very first example where the classical Kepler varieties came in. In rank 2, we have the so-called spin factors on Cn plus 1. Here is the the triple product is a little technical. The rank is 2, and K is essentially the orthogonal group. K always has a rotation in it, because remember by Harishchandra, it was the circularity, that is the torus that is always part of the T. That is the second type. Matrix type, spin factor. Spin factor, the reason is it is generated by a certain spin system. A spin system in quantum mechanics are symmetries having the Clifford relation, something like that. Symmetry is the spin up, spin down, and they generate such a triple. So that's why it's called a spin factor. But then there is the two remaining types, the so-called exceptional Jordan triples. They occur only in dimension 16 in 27. In the first case, rank is 2. In the second, rank is 3. And here A is 8. This means they are really built over the Cayley numbers, over the octonian numbers. So that's why they are called exceptional. And in this case, in the last case, K is the exceptional Lie group E6 up to the T. So the power of Jordan theory is to treat all these cases in a uniform way, in particular the exceptional types. There are many papers in analysis which treat matrix spaces, of course, but avoid the exceptional type. And Jordan algebras, for example, discrete subgroups. In the exceptional Lie groups are much more technical, but in Jordan theory, they can all be treated in a uniform way. We will see this in the proof of my first theorem. I mentioned already Jordan algebras. That is, of course, Jordan, the physicist Jordan. He did not start with Jordan triples. He started with Jordan algebras, namely the anti-commutator of self-adjoint matrices. Let us quickly go over Jordan algebras, although Jordan triples are my main concern. So this time we take a real vector space. That's why I call it X instead of Z. Is called a Jordan algebra. If it has a product denoted by a circle, X circle Y, which is non-associative, but it is commutative. X circle Y is Y circle X. And Jordan's achievement was to find this identity. X squared circle, X circle Y is X. The multiplication by X and by X squared commute. That is his achievement. This is true for the anti-commutator product in an associative algebra. One has to prove it. It's, of course, once it is known, it's easy to check. Well, in the old days of quantum mechanics, people wondered, is this the correct identity that characterizes the observables, the self-adjoint operators in quantum mechanics, the Jordan identity? Of course, that was the hope. So then we would have an algebraic condition of what is an observable in quantum mechanics. Well, with von Neumann and Wigner, another physicist, Eugene Wigner, they studied these questions in the finite dimensional setting. How many Jordan algebras of Euclidean type? Euclidean is a little bit like my Hermitian Jordan triples. A certain trace form has to be positive. How many are there? Are they all given by matrices? And they proved, yes, they are. Every Euclidean Jordan algebra can be realized via self-adjoint matrices of rank R. R is the rank, where K is either the real numbers, that would mean symmetric matrices, or K is the complex numbers. This would be Hermitian matrices. That is what is called usual quantum mechanics, complex Hermitian matrices. K could be quaternions. There are books on quaternion quantum mechanics. Then you have self-adjoint operators over quaternion Hilbert space. So that was the dream of Jordan, that this is all. Then we had the spin factors. Okay, they still behave like an anti-commutator, but then to their surprise, there was one more. That happened only in rank 3, and it happens when you put K to be the Cayley numbers. Cayley numbers were mentioned before. They are 8-dimensional, non-associative division algebra, so I will not write them down. But surprisingly, although the Cayley numbers are not associative, the self-adjoint matrices are still obey the Jordan identity, which is trivial in the associative case, but that was still, so that was is called then the exceptional Jordan algebra. It has dimension 27. How do you see this? Well, self-adjoint over Cayley numbers has 3 components of a Cayley number type, but by self-adjointness you need, of course, real on the diagonal. And here you do not get new degrees of freedom because of self-adjointness. These O's are repeated. So it's 27. So that was very disappointing for these people. Namely, first of all, the Jordan algebra identity does not characterize quantum mechanics. There is one odd example, and it has finite dimension. But of course, we all know in quantum mechanics we get infinite dimension operators. So big surprise, but in any case, that was the start of the theory. For 2x2 matrices, you have these spin factors, and one can write them still as 2x2 matrices. You even don't need an algebra for that. These are formal. So in a sense, all Jordan algebras are Hermitian matrices if you allow the coefficients to include the Cayley numbers. So this mysterious number A that I had, the multiplicity, is exactly the dimension of the K. So real numbers would be A equal to 1, 2, 4, and 8. That is behind the A that I had before. So now I'm leaving this algebraic part. Probably you have heard enough about it. Let us finish, namely, every Euclidean Jordan algebra gives rise to a Jordan triple, but not conversely. Namely, the complexification becomes a Jordan triple by such a kind of trilinear thing. Well, we had seen this before in the spin factor. I wrote down in passing the triple product, so it is a little bit like that. 3 combinations give a triple, and the triples arising this way are called of cube type because of the relation to modular forms. For example, the matrix triple is of cube type only if the square matrix is, if R is equal to S. So now we have a certain background classification of Jordan algebras and Jordan triples. What can we do with it? So now let's come back to the Kepler varieties. I gave you 2 examples of Kepler varieties, namely the light cone and the determinantal varieties. So now let us first define Kepler varieties and then state our first main theorem, that these are normal varieties. This will play a major role in the second part, which is more analytic in nature then. So from now on, we take one of these Hermitian Jordan triples, including the exceptional one, that's very important, irreducible of rank R. It has a rank. It has also these 2 numbers A and B, which are not so important anymore. And fix any number L up to the full rank, from 1 to R. Then the Kepler variety is defined exactly as for matrices, namely all elements of rank less or equal to L. Now you may wonder, what does rank mean? When I introduce the fine structure, it will become clear what rank means, but I can also say these Jordan algebras have determinant functions, similar as for matrices. There is always a determinant function and minors, and in principle, again, the Kepler variety is defined by vanishing of certain minors, which I have to describe in more detail. The regular part, the Kepler manifold, will be, again, where the rank is actually equal to L. That's the dense open subset, and the singularities is the less than L. Now, here comes the first high-level observation, not my observation, but the so-called Matsuki duality. If you have a flag manifold, if you have a flag manifold, let me just write this in GC mod a parabolic subgroup, that means it's a compact, homogeneous scalar manifold. Okay? Then the group G, not GC, GC is transitive, of course. The group G has finitely many orbits, and in particular, it has open orbits, and these are called flag domains, the open orbits. There is also another group inside, namely KC. GC contains both the G and the KC, of course. K is the maximal compact subgroup of G, and there is another orbit, KCO. Okay? Matsuki duality says that there is a 1-1 correspondence between G orbits, not the same O, not the same O. Well, in general, not, but could be G orbits, 1-1 to KC orbits. Or they don't have the same dimension and so on. There is still a 1-1 correspondence. To every G orbit corresponds a KC orbit, which is called a Matsuki dual, and conversely. And what is the relationship? Well, the intersection of the 2 orbits, if we pick a base point, is a K orbit. K sits, so we have GC, here we have G, we have KC, and of course K is in both of them. That is the so-called Matsuki duality. very famous and very extremely, it is the basis of radon transformation, integral geometry in higher dimensions, very famous. And okay, and these Kepler varieties, the Kepler manifolds, are homogeneous under Kc. They are complex varieties, of course, under Kc. They are not compact, they are unbounded, they are not symmetric spaces, and they are precisely the Matsuki duals of open orbits. The Kepler varieties correspond to the open orbits. There is a big project to do it also for other orbits. It comes later, but right now these Kepler varieties have a good setting within this general theory of flag manifolds. Okay, but let us go back to the examples. The spin factors have rank 2, and we recover the Kepler variety that I started with, the quadric. Namely, the degree of the polynomial was also 2, if you remember. For matrix spaces, of course, we recover the determinant varieties. Here's our first theorem. The Kepler variety is normal. Is a normal variety in the sense integral closure. It's a little technical. Normal variety having only rational singularities. Now, what is the point? This result is, of course, classical for the light cone. It's in all textbooks, the standard example of a normal variety. For determinant varieties, and actually for all matrix cases, remember our classification, symmetric matrices, matrix and antisymmetric, Kaup and Zaitsev proved normality for these non-exceptional types by direct computation. But they could not do or did not do the exceptional case, and in particular they did not do it in a uniform conceptual way. So our first result is essentially a proof that is uniform, uses no classification, so applies to the exceptional cases as well, to the two exceptional of dimension 16 and 27, and it is based on George Kempf's collapsing vector bundle theorem. So this I have to explain. The ease of the proof, or the naturality of the proof, is of course because we have all this machinery of Jordan algebras. So I have to introduce a little bit of machinery, all kind of natural, and then the proof will be very straightforward. Namely, remember I wrote the Kepler variety with a polar decomposition. We wrote it as a base S1, and then we had the half line. So we have to generalize this polar decomposition, that's the crucial thing, to the higher rank case. So from now on, of course, Z will be this Hermitian Jordan triple with a triple product. Then a triple projection, or as one says, a tripotent, is an element satisfying triple power u is equal to 2 times u. The 2 is only because I do not divide by half. I could divide by 2, then it would be the usual triple power. So for example, for matrices, this means that u star u is equal to u. That's the condition. These are called partial isometries. Every projection is a partial isometry, but not conversely. This is a triple concept. S sub L is the set of all tripotents of a fixed rank. Remember, I had S sub 1. These are all the minimal tripotents. Well, S sub L is always compact. It's closed and bounded, that's obvious. It is homogeneous under K, not under Kc. It is not a Kc orbit, it's a K orbit. And that is it. It's non-symmetric. Only in very rare cases it is symmetric. In particular, S1 consists of all minimal tripotents of rank 1. So let us look at some examples. Well, I mentioned already for matrices, you get the partial isometries. The spin factor, S1, turns out to be the co-sphere bundle. That was our old friend that I started with, S1. The tangent bundle, both of norm 1. For vectors, if of rank 1, 1 cross D, S1 is simply the unit sphere. And in this case, it's the full boundary, but this is only true in the rank 1 case, the full boundary. They are part of the boundary, these tripotents, but only in rank 1, it's the full boundary. Okay. Every tripotent induces a decomposition of your underlying vector space, similar as when you have a projection. A projection has two eigenvalues, 0 and 1, and it decomposes the space into two pieces. Now, tripotent is like a triple projection, so it has three eigenspaces, namely the DUU endomorphism that we looked at before has three eigenvalues, 0, 1, and 2. And that gives you the Pierce decomposition. I will draw a picture soon. And the Pierce 2 space actually is more than a triple system. It becomes a Jordan algebra, namely it acquires a unit element, namely the U itself, the tripotent. Yes?
So, you said that in general, as one is a part of a boundary, in this example, it's a full boundary.
Because
I think I lost you. Boundary of what?
of the domain D, of the Hermitian domain D, of the unit ball, of the symmetric domain, yes.
Okay, so now...
They all have length 1. They all have length 1, and only in rank 1 is all the unit vectors. That's right. A good question. That's from the domain. So the Pierce 2 space acquires a unit element, namely the U itself, and the multiplication is simply you look at the triple product and put the U inside. So what is the Pierce decomposition for a matrix? It's very easy. If U is the basic tripotent, namely you take a number of ones along the diagonal, that is what you would do for projections, okay? Then the Pierce 2 space is precisely this corner. That is the Pierce 2 space. The Pierce 0 space is over here, kind of opposite, and the rest is the Pierce 1 space. So you see it's a little bit like a projection decomposition, but you need, obviously, you need three pieces. The Z1 becomes reducible in this case, but Z0 and Z2 are always still irreducible. So that is the Pierce decomposition, a natural concept once one has a little experience. So now we prove the normality theorem. We have all our ingredients, and all the work has been done by George Kempf. Namely, we all know the Grassmannian. It turns out that the Grassmannian and flag manifolds make sense way beyond linear algebra, namely for these Jordan triples. Namely, we take a quotient of the tripotents, SL modulo an equivalence relation, namely the set of all Pierce 2 spaces of a fixed rank L. So we do not take the tripotents themselves, but we identify two tripotents of same rank if they have the identical Pierce 2 space. So for example, of course, every unitary in this little piece has the same Pierce space. It need not be the 1, 1, 1. Every unitary operator has the same Pierce 2, and so this is the collection of all Pierce spaces, just like a Grassmannian. But you do not take all subspaces of Z, but only kind of Pierce 2 subspaces, very special ones. It turns out that it is a compact Hermitian space, symmetric space, both a K orbit and a KC orbit, just as the Grassmannian is as well. And it is precisely the center of the open orbit. Here, this is the open orbit, and the Grassmann is precisely the so-called center, the Matsuki center, the intersection of the two. GO intersecting KCO. That would be the Jordan Grassmann manifold. It always sits at infinity. We have to be careful. It is not fine. It always sits in the plane at infinity. Define the tautological vector bundle just as you would do for Grassmannians, namely, over each point of ML sits the space itself. That is what you would do tautologically. Now, this is a homogeneous vector bundle, namely, you fix a tripotent and take its canonical PS2 space and let L be all elements in KC which fix this PS2 space. Then the tautological bundle becomes homogeneous, and the mapping that sends U into its inclusion. U has rank, these have all rank L. If this is the number L, the full PS2 space has rank at most L. That's obvious. Has rank at most L. So that is a so-called collapsing map in the sense of George Kempf. And his theorem is the range of a collapsing map for a homogeneous vector bundle is a normal variety. And that's it. That precisely fits in our setting. Now, how about the birational isomorphism? Well, you take the invertible elements in each fiber. That's open dense, Zariski dense subset. And on the invertible elements, the tautological bundle becomes a disjoint. They become disjoint. Different Perl spaces cannot overlap in invertible elements. That is not possible. On the invertible elements, it's disjoint, and that becomes my birational isomorphism. I think there is a little circle here missing. This is the interior. This must be the interior. So I'm sorry, this is missing. So it has only rational singularities. That is the proof of the first theorem. So the main point is all the machinery is perfect to apply Kempf's theorem. Not only in this case, but also for much more general flagged varieties could I do this if I wrote down all the details. Okay, so but now time is running late. Let us come to the second and more analytic part, to the TYZ, Tian-Yau-Zeldich expansion. If you have a compact Kähler manifold and your symplectic form is integral, you have a pre-quantum line bundle L, whose curvature gives the omega, and you look at the holomorphic sections for large enough powers, L to the nu an integer, going to infinity. Then Kodaira, or the physicists would say coherent state embedding, is you take the projective space over the sections, take a basis of sections, and evaluate at the basis. That gives you an element in the projective space. The projective space has the Fubini-Studi metric of size d sub nu, where d sub nu is the domain, the dimension, and you dd bar log of the inner product on Pn is the Fubini-Studi metric. So you pull it back via the Kodaira embedding, kappa nu star, kappa nu was the embedding, and then it will differ from omega. It will become a symplectic, it will become a Kähler form on M, but it will not be identical to omega, more precisely nu times omega, because you took the power L to the nu. And the difference is the so-called Kempf distortion function. So that's the precise formula, dd bar log T nu, and T nu can be written in terms of this distortion function. So the distortion function measures how far apart is the quantum symplectic form, namely coming from the Kodaira, from the classical symplectic form. And of course, only for projective space itself, also it's identical, but in general, there will be this. But Tian-Yau-Zeldich expansion says that there is functions, we will prove they are polynomials in our setting, aj of z, depending on the base point, of course, such that the Kempf distortion function has this asymptotic expansion that I wrote down over here. That is the usual form. It's not a convergent power series, it's an asymptotic expansion in a somewhat technical case. Okay, so that applies to compact Kähler manifolds. But our Kepler varieties are non-compact. They are never compact. They do not extend to the projectivization, or they are only affine varieties. So for non-compact Kähler manifolds, we need infinite dimensional Hilbert spaces of holomorphic functions. These are finite dimensional. That's the main difference. that we encounter now. So let us define these Hilbert spaces. Namely, I have to go a little faster now, I'm sorry, but all the basic things are in place. Every Jordan algebra X, remember I gave you the list, Hermitian matrices over Cayley numbers and so on, has a symmetric cone, namely all squares of invertible elements. And another theorem of Köcher-Winkelberg actually says that Jordan algebras are in 1-1 correspondence to symmetric cones. Now the cone is essentially kind of positive definite matrices. For the spin factor, we obtain the light cone. Now, for every fixed tripotent now, we look at the cone in the little piece, in this corner, in the Pierce 2 spaces. This becomes, as I mentioned, a Jordan algebra. It has a symmetric cone, I wrote it down one more time, of rank L. This will be of rank L. It's for L equal to 1, it's only a half line. And proposition is, the Kepler manifold has a polar decomposition where the base is the tripotence and the fiber is the cone. That replaces the polar decomposition that I had before, where the base was S1, the minimal tripotence, and the fiber was a half line. So the half line is now replaced by a symmetric cone. Half line is of course a cone of dimension 1 or of rank 1. So using this polar decomposition, we can now, this becomes now a little bit more analytic, I'm sorry, radial measures. You look, maybe I should draw a picture of this polar decomposition. You look at any measure on a symmetric cone. So, for example, on a half line, if you start with a basic case of, so this would be my cones, and here is the tripotent, roughly like that, okay? The full thing is the Kepler manifold. You can write down a measure on the full Kepler manifold by Fubini's theorem. It's essentially Fubini type theorem, using the fibration that I had. For L equal to 1, the radial part is just dt from 0 to infinity. So they are really functions on the half-line in one dimension. Using such a measure, you can define a Hilbert space of holomorphic functions, namely all holomorphic functions on the Kepler variety, which are square integrable. That is a Hilbert space. You do not have to pass to the closure because this is already a complete Hilbert space because of holomorphy. Well, we have to exclude the trivial case where we do not have a variety at all, namely if the rank is maximal, then of course the Kepler variety is dense. This is not so interesting. Let us exclude this case where we would have a Jordan determinant. Apart from this, we have the extension theorem, namely every holomorphic function on the Kepler manifold has a unique extension to its closure. Proof? Well, the singular set, remember, is the union of the Kepler varieties of lower rank, and it is easily shown that the codimension is at least 2. The dimension of these Kepler varieties are of course known, but the normality theorem, using a result of Lojasiewicz, the second Riemann extension theorem, namely for codimension 2 singularities, holds for holomorphic functions, and that is already all. So you see, again, normality, that is the main reason why we need normality, of course. So now we have this is now a little technical. We need some representation theory. Yes?
So, did you say that the measures on the cone are finite measures?
Of course, we want the Hilbert space to have non-zero, not non-zero. Let me show the two examples that we have, then they will be finite, okay? We need some background on representation theory of the compact group K. Namely, look at all the polynomials on my Hermitian triple Z under the group action of K. The polynomials have a multiplicity-free decomposition. That's a very famous theorem by Schmidt. Well, Constant claims he proved it first, and the first calculations were done by Hua, so let's call it Hua-Schmidt-Constant decomposition, into irreducibles indexed by partitions. So every partition, every Young diagram of length L, R, so partition is a Young diagram with R, with at most R rows, gives rise to such an irreducible decomposition, K module, and it is completely uniform for all Jordan triples. I proved that the highest weight vector can be described by Jordan theoretic determinants, and the dimension d sub m is explicitly known. Now, let us look at the Fisher-Fock inner product. This is the standard inner product for entire functions. Then the exponential e to the inner product zw, because of this expansion, is uniquely a sum of finite dimensional kernel functions, denoted by em of zw, related to the PMZ. Only in the rank 1, they are very easy, namely the power zwm over m factorial, of course, from the exponential function, but in general, they are more complicated. Using the characteristic multiplicity that I had, we defined the Pochhammer symbol as a quotient of gamma functions. That's a combinatorial number that is well known in analysis. And the extension theorem says that my Hilbert space of holomorphic functions is the Hua-Schmidt-Constant sum, but involving only partitions of length less or equal to L, since the other components vanish on ZL. And the first theorem, which I just want to mention in passing because I have a better theorem soon, is that the reproducing kernel function can be expressed in terms of these Fisher-Fock kernels, Em of ZW, and the numbers are explicitly known. Dm is the dimension and Em is the kernel. Here we have a similar one using the minors, but of course the dimension shows up in an ugly way, although they are known in an ugly way. So this I will improve in the next slide. That may be, then I have 2 slides and I will be done. Namely, I mentioned already that every Jordan algebra has a determinant, essentially given by Cramer's rule, namely the exact denominator of the inversion map. So it's not always the determinant, sometimes it's the Pfaffian or the Lorentz metric. And let delta n be the associated constant coefficient differential operator of order R, if the rank is R. Then n of x times delta n is a kind of Euler operator. And using these Euler operators, I write down a terrible operator here, a product of Euler operators of very high order for this on a symmetric cone omega L, in particular on the half line. Well, it's a little fast now, but this is kind of a natural differential operator, homogeneous of a certain order. And now I can express our main result, which I would have to elaborate in special cases, of course. Our main result is that the reproducing kernel can be expressed in closed form. That means not via the Taylor expansion, but in closed form. In the following sense, K rho, at least on the diagonal, that is enough, is this differential operator applied to a special function of hypergeometric type. So we find a hypergeometric function in several variables, of course, and I will write down in 2 examples where I can do it, okay? Now, hypergeometric functions have good asymptotic expansions, quite difficult to establish, that's our main task. this will lead to the desired expansion of TYZ type. So what is a hypergeometric series of type PQ? You probably know the ordinary F21, so this is the general, where the powers are replaced by the kernels EMZW. That would be a general hypergeometric series, okay? Now we have two theorems, let me just mention them. Let us first look at the first metric. Here we had asked what kind of metric and inner product do we need. Let us first look at a simple plurisubharmonic function, namely ZZ to the alpha, and then omega dd bar phi is the associate Kähler form. Then the measure that I want is this one here, which I can write down explicitly. And then the theorem is that in this case, thank you. The theorem is that in this case, in the Fock space situation, we get an F11, a confluent hypergeometric function with certain parameters, dl over L, n over L, at the power nu t. You know it must depend on nu. We want an asymptotic expansion in nu. So the nu t is just the argument inside the hypergeometric function. So that is the first result in the Fock space. And as I said, it leads to the TYZ expansion. This would become more technical. I have one more, and then I'm finished. Namely, I look at the Kepler ball, which will be the intersection of the Kepler variety with the unit ball. And in this case, I take another plurisubharmonic function, the determinant of the so-called Bergman kernel, which I did not have time to define, but it can be written very explicitly. So this is the standard Bergman space on the domain D, but here we have it on the Kepler variety. Again, we can take the associated radial measure, has a nice polar decomposition, and this time we get an F21. So same theorem as before, but in the Kepler ball, the reproducing kernel is a DL, this universal differential operator, and then an F21. So let me finish. There is a very nice and strange pattern. The Fock space on the full vector space has F00. That was more or less by definition, namely the exponential. The Bergman space on the domain D has F10. That's the famous Faro-Couragny formula. Passing to the Kepler manifold, well, we have to introduce this universal differential operator, and we get an F11. Passing to the variety makes it more complicated, of course. And finally, passing to the Kepler ball, we started with F10, and now we get an F21. So somehow interesting pattern. And as I said, this will, because the asymptotic properties can be established, this gives rise to rather explicit expansions of TYZ type. And let me thank you for this. Thank you. Yes?
So when one looks at the Tierney-Zeldich asymptotic expansion, and one looks at, if one fixes a fiber and one looks at the first coefficient, then one picks up the scalar curvature.
Yes.
Presumably the other coefficients have other geometrical interpretations, but at least for the first one,
Yes.
this curvature is visible. So in this situation, I know you didn't have time to talk about it, but since you said that one can bring hypergeometrics into the picture, those have a nice asymptotic expansion.
Yes.
Do the leading terms encode some sort of geometry?
Of course, yeah. We get rather explicit polynomials, not only for the leading term, but you are right. I should have written down and worked out the leading term, but we get a finite sequence of polynomials. So it's not just the leading term, but completely right. Of course, in the first case, it depends on the alpha, on the power alpha. The curvature will depend on the alpha, and it might be a good project, really, to work it out what it means geometrically. We have not done this so far.